Hi, welcome back to a new lecture from Transformers for Vision series. In today's lecture, we will be diving deep into the self-attention mechanism. But unlike last lecture where we implemented a simplified version of self-attention mechanism by just taking the dot product between the vectors, this time we'll be implementing self-attention with trainable weights. And when I say trainable weights, I specifically mean the weight matrices associated with key, query, and value. So these are terms which you will find in the context of large language models. So I hope to give you a good amount of intuition about what is key, what is query, what is value, etc. The self-attention mechanism that is used in LLMs like GPT is also called as scaled dot product attention. So by the end of today's lecture, you should also understand what is the intuition behind this equation which was mentioned in the Attention is All You Need paper. Right now, it may look a bit intimidating to you, but don't worry. By the end of the lecture, I guarantee that you will have a fairly good understanding what exactly this equation is trying to tell from an intuition perspective. So with that, let's get into the lecture. So first, let's take a step back and try to understand what all we have been discussing in this course so far. In the lecture before, we discussed about simplified self-attention, where we constructed attention scores by using dot product between the vector embeddings. And even before that, we started our discussion by going through Badano attention, which was introduced in 2014. So as we know, Badano attention was used primarily in the encoder-decoder architecture in neural machine translation, where every single hidden state in the decoder had access to every single hidden state in the encoder. So these H1, H2, H3 are hidden states in the encoder. And all these states were accessible in the decoder, which was not the case before Badano attention. And because of this, instead of relying on one single context vector which comes out of the encoder, you can rely on every single hidden states. And you can construct relative importance that the decoder should pay to each of these hidden states. That way you are taking off the pressure that you were putting on the final context vector. If you don't remember the encoder-decoder architecture from recurrent neural networks, don't worry, it's not of relevance for today's lecture, but I just wanted to give a brief recap. If you really want to understand how Badano attention came into picture in 2014 in the context of neural machine translation, you can go back to the lecture in which we discussed about how RNNs started with encoder-decoder architecture and then eventually attention mechanism came into picture. Now, in self-attention, however, what we were trying to do was something different. We had one input sequence, and let's say this is our input sequence, dream big and work for it. We wanted to construct context vectors corresponding to every tokens in the input sequence. For simplicity, we are now thinking that each token is one word, although in reality, in models like GPT, it uses byte pair encoding. So one word is not necessarily one token. There could be characters and subwords. But here for simplicity, what we want to do is in this sequence, you have 1, 2, 3, 4, 5, 6. So there are 6 tokens. And for every single token, we want to produce a corresponding context vector. If this was a neural machine translation task in the encoder-decoder architecture of NMT, we would have just produced one context vector at the end of the sequence at the output of encoder. And we were hoping that that context vector will embed whole information present in the sequence. But with the advent of self-attention mechanism, we don't have to do that anymore. We can calculate how much each word in the sequence should pay attention to or should attend to every word in the same sequence. So that's the reason why the name self-attention came into existence. So in today's lecture, we'll be considering these tokens as 3-dimensional vectors so that we can easily plot like this. In the previous lecture where we implemented a self-attention in a simplified fashion, we had input embeddings like this: dream, big, and work for it. So dream, this is the original input embedding for dream. This is the embedding for big, and work for it. Now to calculate how much attention dream should pay to big, or how much, let's say, work should pay to big, what we did was we took a dot product between these two vectors, and based on the magnitude of those dot products, we constructed attention scores. So if there are 6 words, and if we consider big as the query meaning the token that we are currently looking at, we can construct six attention scores: one between big and dream, one between big and itself, one between big and, then big and work, big and for, and then big and it. Now these attention scores are not normalized. So what we discussed in the earlier lecture was that we normalize these attention scores such that they add up to 1. So we were using softmax function for normalizing such that the 6 attention scores corresponding to any query. So in this case, if we consider our query being big, there will be 6 attention scores corresponding to every single key. So let's say this is 0.1, 0.2, 0.2, 0.1, 0.3. So that will be 4 plus 1, 5, 6, 7, 8, 9. And then this will be 0.1. Now, if you add up these numbers, there are 6 numbers. And if you add up these, it will be 1. So 0.1 plus 0.2 plus 0.2 is 0.5, 0.6, 0.7, 0.78, 0.8, 0.9, and then 1. So you can view this as percentages. Our sentence is dream big and work for it. Now what this means is dream should pay 10% attention to big. I mean, big should pay 10% attention to dream. Big should pay 20% attention to itself because this is 0.2. Big should pay 20% attention to and, etc. So by having these normalized attention scores, we can have intuition on how much percentage attention each query is paying to every single key in the same sequence. So this is how normalization of the attention scores lead to something called as attention weights. So these numbers, which resulted from softmax calculation, are called attention weights. Now to construct the context vector, what we did was we multiplied the original input vectors. So dream had an original input vector, which was this guy. Big had a vector for dream big and work for it. So each input vector, so if I denote these vectors like this, you can scale these vectors using these attention weights. So you multiply the vector with the corresponding attention weight and then you add them up. That is how you get the context vector for, let's say, the word big. Similarly, if you take the row from the attention matrix, which are the attention weights corresponding to any particular query, you can take attention weighted sum of the input vectors to get the context vector. So now if we plot the context vector here, this was the context vector for the token big, which we got at the end of the previous lecture. But you must have noticed one thing. We know that in large language models, training the model is a big deal. But here in this attention calculation, in the self-attention calculation, there is no training involved. There are no weights that are trainable. The dot product is simply taken between the vectors which we already have. So after tokenization, we have the vectors corresponding to tokens. And then there is no more trainable weights involved. We are simply taking dot product to get the attention scores. Then we are normalizing it using softmax to get attention weights. Then we are taking weighted attention of keys corresponding to any given query to get the context vector for that particular query. So this is what we were doing in the last lecture. If you want to really spend some time on simplified self-attention, and if you are watching this lecture for the first time in the series, please go back to the previous lecture just to spend some time on simplified self-attention so that you can get much better intuition on why we are interested in constructing a context vector. In very simple terms, context vector is very important because it has much better meaning embedded in it. So it's much more enriched. So the context vector for big is much more useful to us, or is much more useful to the large language model than just the input embedding for big. Because the context vector for big is also taking into consideration the fact that there are other words in the sequence. There are these remaining 5 words also in the sequence. So this is why context vector is much more information rich or context rich. Now, if you just look at this diagram, this is again just the summarization of simplified self-attention. We had the input embeddings corresponding to every single word or every single token. So we had 6 tokens. So these were the 6 input embeddings, or basically the 6 3-dimensional vectors. Then if we consider big as the query, which is the second token. So we are looking at how much attention should big pay to dream, how much should big pay to itself, how much should big pay to and, etc. We took dot product between big and dream. So it'll be just one number, scalar. So these dot products denoted by omega 21. Omega 21 means the attention between dream and big. Omega 22 means attention between key number 2 and query number 2. Omega 23 is attention between key number 3 and query number 2. Like that. So we got these attention scores, which are denoted by omega, and then we got attention weights, which are denoted by alpha. And these attention weights should sum up to 1. And then we use these attention weights such that we took a weighted sum. So alpha 21 was multiplied by the input embedding. Alpha 22 was multiplied by the input embedding for the second query. Alpha 23 with the third one, for the second token. Alpha 23 with the third token. Alpha 24 with the fourth token embedding. And then we add all of that up. So it's as if you are adding all these 6 vectors, but we are not simply adding it. We are adding it by multiplying with a scaling factor. Scaling factor is these attention weights. So this is what we did in summary. Now, just look at what all things did we use. We simply used a dot product. Dot product does not involve any weights, right? We are using already existing numbers. So in today's lecture, we are going to introduce weight matrices, which will allow a neural network to train, and then these weight matrices will become better and better such that when you are taking a dot product, after performing some sort of transformation to your input embeddings, you will have a better context vector available to you. So the end goal is to have an even better context vector. We already got a context vector for the word big, for the word dream, etc. in the last lecture, but we want to get an even better context vector. And these trainable weight matrices are so crucial in large language models because these weight matrices are those that help us produce these context-rich vectors. And these weight matrices are known by the name query matrix, key matrix, and value matrix. So query, key, and value are terms which you might have heard of in the context of LLMs, but you probably don't have a great intuition about this. So don't worry, we will be paying enough attention to the logic of why these matrices were introduced and what exactly do they do to the input embeddings and how exactly it results in a much better context vector. So now with this much information, let's try to actually get into the lecture where we are now going to see how can we transform the input embeddings before we take the dot product so that we have some better attention weights, and then how can we use that attention weights to create a better context vector. Now you might have a question, what is wrong with the idea of dot product itself? Isn't it logically correct to take dot product? Yes, that idea is fundamentally correct, because if two vectors are in general pointing in similar directions, it means semantically they are related to each other more than, let's say, two vectors that are orthogonal to each other, because we know that the vectors are pointing into certain directions in this multi-dimensional space or three-dimensional space in our example, such that the direction of pointing has some significance. And the magnitude of these vectors are not all the same. They are different. The magnitude depends on how much information these vectors can give us. So for words like is, the, a, etc., which are very frequently occurring words in sentences, which does not give us any specific information. The magnitude of the vectors corresponding to these tokens will be very small. Whereas if we consider, let's say, words like quantum, these are not words that typically occur in our sentences. So the token corresponding to the word quantum will definitely have a bigger magnitude. The vector will have a higher magnitude. But the direction has definitely semantic significance. So fundamentally, the idea behind taking dot product is still valid. Why? Because if two vectors are generally pointing in the same direction, then maybe they should pay better attention to each other. And the best way to indicate this is by taking a dot product, because dot product of between two vectors that are pointing in the same direction will be a bigger number. Dot product between two vectors that are perfectly orthogonal to each other will be 0, because the dot product will be vector A times vector B times cosine of angle between them, and cosine of 90 degree is 0. So this idea makes sense. But the problem here is in the fact that we are taking the direct dot product of the input embeddings. That is where the issue is. So now what we are trying to do in today's lecture is we have to do something to the input embedding to transform it before taking the dot product. So read the sentence. We want to take the dot product. However, instead of directly taking the dot product of the input embeddings, we take the dot product of some transformed versions of the input embeddings. And how do we transform? This is exactly where the trainable parameters come into picture. So we transform these input embeddings using 3 matrices. So we usually denote those matrices using the terms WK, so weight matrix corresponding to key, weight matrix corresponding to query, and weight matrix corresponding to value. So these matrices define how we have to transform the input embeddings before we can take a dot product. Now, what is the meaning of this key, query, and value matrices? We'll get to understand that in the course of today's lecture. But here is a numerical example which might help you better understand what is the problem with just the vanilla dot product. Let's say you have this sentence: the dog chased the ball, but it couldn't catch it. Now here, this it word should pay more attention to what? This it refers to ball. So here, this it means dog. Couldn't catch, it means that the dog couldn't catch the ball, right? So this it is ideally more connected to ball than to the dog. Now let's say we want to construct attention scores between dog and it and ball and it. And let's say in the 3-dimensional space, these are our vectors. So dog is 0.9, 0.1, 0.1. Ball is 0.1, 0.9, 0.1. And it is 0.5, 0.51. Now the dot product between dog and it will be 0.9 times 0.5 plus 0.1 times 0.5 plus 0.1 times 0.1, which results in 0.51. And same dot product results when you take the dot between ball and it. Same thing. So although the input embeddings are different, so these are 3 different input embeddings. When you take the dot product, the attention scores between dog and it and ball and it are exactly the same. So somehow taking the simple dot product from your basic input embeddings are not working here, right? So this is just a numerical example, which is oversimplified, but it drives home the point that you should not be taking the direct dot product between the input embeddings if you want to avoid situations like this. So this is where the solution was introduced, was you transform the input embedding. So you transform queries using Q, the WQ matrix. You transform keys using a matrix called WK. So these are weight, W for weights. So this is the weight matrix corresponding to key. This is the weight matrix corresponding to query. And these are learned matrices. Why do we call it as learned matrices? Because the numbers inside these learned matrices will change as we train the large language model. Now, let's say after training my large language model, I got this weight matrix, Q, and then this weight matrix for key, WK. Now, what happens if I transform my dog vector using WK? How do we transform first of all? So here, the dog vector had a dimension of 1 by 3. the weight matrix has dimension 3 by 3. So the dog vector multiplied by weight matrix will give us again 1 by 3 matrix multiplied by 3 by 3 matrix will result in a 1 by 3 matrix. So this is now having the same dimensionality as that of the original dog vector, but it has transformed in values. So when we multiply the key weight matrix with the original input embedding for dog, we get 0.9, 0.2, 0.1. And when we use the key weight matrix with ball, we get these numbers. Now, the query that we are looking at is it, because we want to see how much attention it has to pay to dog and how much attention it has to pay to ball. So now query is it, which means it is transformed using WQ. And WQ is this matrix. So if you multiply this matrix with the original input embedding for it, which was 0.5, 0.5, 0.1, you get something like 0.5, 0.5, 0.1, because here you might notice this is just an identity matrix. Now, if we try to calculate the attention score, if you take the dot product between the transformed it vector and the transformed dog vector, you get the number 0.56 if you take dot product between these two vectors. And similarly, if you take a dot product between the transformed it vector and transformed ball vector, you get the attention score or dot product 0.96. Now you see this attention score is capturing the fact better that it should pay better attention to ball than to dog, right? So how did this happen? Because we transformed the original dog vector, original ball vector, and original it vector using key matrices or query matrix, depending on which one is the query. So this gives you an intuition that indeed this transformation is useful, because if we do the transformation in the right way, our attention scores can be much more meaningful. Now, this is what we are going to discuss in today's lecture, but please remember this part of this figure. We are trying to solve the problem of context vector not being able to capture the dependencies in the sequence that well if we directly use the input embeddings for the dot product. So that problem we want to solve. So before the dot product, we want to transform the input embeddings. Now, by paying attention, what we mean is we are able to selectively access parts of the input sequence. So what do I mean by that? Here, it is selectively accessing ball more. How? Because the attention score is 0.96 than the word dog, because attention score between it and dog is 0.56 after transforming, right? So paying attention is simply a fancy way to say you are attributing more importance, or the current query is attributing more importance to this particular key than other key. All right. So far, so good. Now let's try to understand how exactly are we going to transform our input sequence using these matrices. What are the dimensions of these matrices? Then what are the outputs we get? And then what do we do with these outputs to finally get our context vector? So our end goal is to get a very good context vector. Okay. Now we are going to look at two example sentences. The first example sentence we'll focus on while understanding the theory of the query key and value. And then we'll take another example sentence while implementing the same in code. So the second half of today's lecture is entirely dedicated to us implementing the whole self-attention with trainable weights in code. Don't worry if the code looks intimidating. I'll walk you through step by step. So first, let's see what happens to our input embeddings. So this is our input embedding. The sentence that we are considering right now is the dog chased the ball. Now this sentence is split into 5 words. So we are considering each word to be one token. So we have 5 tokens. The dog chased the ball. So that is this first dimension over here, 5. Now each token is embedded in a 3-dimensional space. So the total number of, if this were to be represented as a matrix, it will be of dimension 5 by 3. 5 denotes the total number of tokens. 3 denotes the dimension of each token. Now, what we are going to do is we are going to now transform each and every one single of these input token into another space, a space that is having different dimensions. So the other space to which we are going to transform this using our trainable weight matrices may have a different dimension. So currently in this example, we are going to consider that space to have a dimension of 2. So instead of 3-dimensional space, now we are going to transform these 5 input tokens into a 2-dimensional space, right? So we have input tokens of size, we have 5 input tokens, each of them of size 3 dimension. And this is being now transformed into a 2-dimensional space. But we have 5 tokens, which means what we will end up is something like 5 by 2. So we introduce 3 matrices, one called query matrix, one called key matrix, and one called value matrix. These matrices perform the transformation of these input tokens into the 2-dimensional space. So if you multiply this matrix, dimension is easy to understand. So this Q matrix, WQ matrix has a dimension of 3 by 2. So if you multiply a 5 by 3 matrix with a 3 by 2 matrix, you will get a 5 by 2 matrix. What is this? These are the transformed embeddings of every single input token in the query space. Query space has a dimension of 2. So these are the 5 transformed embeddings of every single input query. Dimension of each query now became 2 instead of 3. Similarly, the key matrix also has the weight matrix corresponding to key also has a dimension of 3 by 2. So if you multiply 5 by 3 matrix with 3 by 2 matrix, you get a 5 by 2 matrix. So now this is the key space, which is also of 2 dimensions. And every single key is now a 2-dimensional vector. So there are totally 5 vectors. So this dimension is 5. Same thing happens for value. Now key and query are easy to understand because we have discussed so far what is a key. So if we are considering how much attention should dog pay to all the words in this same sequence, then dog should maybe pay 10% attention to the, 20% attention to itself, 30% attention to chased, some X% attention to the, and some percentage attention to ball. So here dog is the query and all the words in the same sequence are the keys, right? So we know what query and key is, but we don't know what value is yet. So we'll come to that, but I hope you understand now what are these transformed queries and transformed keys. It's simply some transformations happening to the input embeddings such that the dimensionality reduces from 3 to 2. Now what we can do is, let's look at this in terms of some numbers, okay? So that you can better appreciate what's happening here. So your input is 3 dimensions. So you have 1, 2, 3 dimensions. So 3 numbers to denote every vector. So this is the vector for this is the vector for dog. Like that, you have 5 vectors. So 5 by 3. Now let's say we have a trainable weight matrix corresponding to query. So WQ. And it's of dimension 3 by 2. So these are the 6 numbers corresponding to your trainable weight matrix for Q. Similarly, you have 2 more trainable weight matrices, trainable weight matrix for key, trainable weight matrix for value. Then you multiply this 5 by 3 matrix with a 3 by 2 matrix. So this X is the input vector, X times WQ. So this is not multiplied by symbol. This is just X. Okay. So X times WQ will result in the query matrix. Query matrix is nothing but the 2-dimensional representation of your input queries. So this is the 2-dimensional input, 2-dimensional representation corresponding to this is corresponding to dog, chased, then the ball. So earlier it was a 3-dimensional representation. Now it became a 2-dimensional representation. Same thing happens for key, but these numbers will be different. So the key matrix will be different from query matrix because the weights, the matrices that transform the input embeddings into Q and key are different. So these WQ and WK are 2 different matrices, which means the key corresponding to dog, chased, the ball, the key values will be different from your query values. See, 0.86, 1.22, Here it is 1.07.82. Now earlier in simplified self-attention, what did we do? If we wanted to calculate how much attention dog should pay to the, what we did was the query we multiplied with key. So if we want to know now how much attention dog should pay to the, we take this number 1.00, comma 0.07, 0.70. So this is the query vector corresponding to dog. We did a dot product between this and the key vector corresponding to the. So that was 1.07, comma 0.82. So when you do dot product, this times this plus this times this, you will get one single number, correct? So what you can do is, for dog, you can calculate attention it has to pay to the, attention it has to pay to dog, attention it has to pay to chased, attention it has to pay to the ball, etc. Similarly, for every single key, you can calculate an attention score corresponding to every single, for every single query, you can calculate an attention score corresponding to every single key. Which means at the end of the day, if you have 5 vectors in your input, you will have 5 by 5, 25 attention scores as the final output. And how do you get 25 attention scores from this 5 by 2 matrix, which is key matrix, query matrix, and 5 by 2 matrix, which is key? You can simply do Q multiplied by query transpose. And when you do that, when you do Q multiplied by query transpose, the result is you are multiplying a 5 by 2 matrix with a 2 by 5 matrix, because you are taking transpose of key, which is 5 by 5. So that is what you will get. So here, this is the 5 by 2 matrix corresponding to query. This is the 2 by 5 matrix, which is the transpose of key. You multiply these two to get the 5 by 5 matrix, which is now the attention scores. These are not the attention weights, these are the attention scores. Now you might notice one thing with these attention scores. Now these are the dog chased the ball. So now if dog is our current query, these are the attention scores that dog should pay to each and every word in the sequence. So dog should pay 1.57 attention to the, 1.71 attention to dog itself, 1.89 attention to chased, 1.26 attention to the, and 1.97 attention to ball. But these are attention scores, so these numbers do not add up to 1. But if these 5 numbers were adding up to 1, it was easy for us to say dog must pay 20% attention to this particular token or 10% attention to this token. So it's more interpretable. And if these numbers are very nicely between 0 and 1, it's also really good for training, because for training stability of neural networks, it's better to have normalized numbers. So what we have to do is we have to convert these attention scores into attention weights. So what we do is, firstly, let's pick up the attention score for just ball. So what are the attention scores corresponding to ball? We should have 5 numbers. So just to go back to our earlier diagram, the conceptual diagram. So we were here, we had input sequence using query, key, and weight trainable matrices. We converted this into query space. So all the 5 input embeddings were converted into query space, which had only 2 dimensions. We also created all the input tokens were converted into key space with 2 dimensions, and also value space. So far, we haven't discussed about value yet, but we'll come to that, right? But for this conversion, what did we do? Simply, we multiplied the input sequence with WQ, WK, WV. So that resulted in query vector, key vector, and value vector for dream. Same for big, same for and, work for it. So this is a different sequence. The sequence that we are currently discussing is the dog chase the ball. But for any sequence, this is essentially how it works. You take the tokens in the sequence, you multiply individual tokens with W matrices. So if you multiply the input token with the WQ, you will get Q of 1. Of 1 means of the first input token, X of 1. Similarly, if you multiply x of 5, which is the fifth item in the input sequence with wq, you get q of 5, which is the fifth query vector. Then what we have to do is we constructed attention scores. So to construct attention scores, we did not use value vector at all. So value vector we are still not looking at. So just ignore this part for a moment. What we did was we simply took a dot product between query vector and key vector. So if we want to calculate the attention between, let's say, query, which is big. So in this sentence, so this is a different sequence, but same example. If the sequence is dream big and work for it, which is the same sequence that we are going to use in our example code, dream big and work for it. Here, if let's say our query is big, we just want to calculate how much attention big should pay to dream and work for it, as well as to itself, to big itself. Then we want to do the dot product between q of 2 and k of 1. Q of 2 is the query in the second item, which is query corresponding to x of 2. K of 1 is key corresponding to the first item in the sequence, which is key corresponding to dream. And then we get the attention score. So this is the attention that big has to pay to dream. Similarly, this is the attention big has to pay to 4. To get the attention, we are simply taking the dot product between query and key. Okay. Now, so far so good, but these are attention scores. So these omegas do not add up to 1. And we saw that kind of in this example. So here, these numbers do not add up to 1. Now, if we take attention scores for ball, these are the attention scores corresponding to ball. So now we are back to our original sentence, which is the dog chased the ball. Now for this sequence, if you add up the numbers, it's not adding up to 1. So what we do is, here is where we introduce the idea of scaling and softmax. So scaling is done for a very particular reason, which I will discuss in a moment. But by scaling, what I mean is these numbers are divided by square root of d, where d is the dimension of the key space. So please note our input dimension or input embedding space in our example had a dimension of 3. It was a 3-dimensional space. But the key space or query space or value space, the dimension is 2. So we are dividing these numbers by square root of 2. So when you divide by these numbers, you get now the scaled attention scores. So these are scaled attention scores. Now these attention scores again do not add up to 1 because we are yet to convert it into softmax probability distribution. So we convert it into softmax probability distribution using this formula, e raised to xi divided by sigma e raised to xi. So when you do that, you get your attention weights. So now these attention weights are numbers which will add up to 1. So this is how you go from these numbers. So these are attention scores. You go from attention score to scaled attention score. And then you go from scaled attention score to attention weights. And these attention weights are now numbers that will scale, add up to 1. Now you can say, so here ball is my query. Okay, because we are now just focusing on what happens to this one row corresponding to ball is the query. Now these scale attention weights tell us ball should pay 17% attention to the first token. First token is the. It should pay 19% attention to second token. It is dog, right? So it was the dog chased the ball. So ball as a query should pay 17% attention to the, it should pay 19% to dog, it should pay 23% attention to chased, 13% attention to this second the, and 29% attention to itself. And when you add this 29 plus 13, 42, 52, 62, 65, 75, 84, and then 94, 101. So I think it's 101 because we have rounded off certain numbers. So this is how you construct attention weights. Now, so far it's good, right? So now let's go back to our original diagram. We are not still discussing about value, but we'll come to that in a moment. But let's just go back. So you got attention scores, and attention scores were the result of the dot product between Q and key transpose. Q was 5 by 2 because you had 5 vectors. The dog chased the ball. 2 because the query space has a dimension of 2. Key space has a dimension of 2. Value space has a dimension of 2. Key transpose will be 2 by 5, right? And then when you multiply these two matrices, you get 5 by 5. Now these are attention scores. These are the attention scores for the query these are the scores for dog chased the ball. All right. Now these attention scores, if you consider query for ball is simply ball is first of all a 1 by 2 vector now in the query space. But key matrix is 2 by 5, right? So key matrix here, key transpose matrix was 2 by 5. And query for ball was this guy. So if you simply multiply just this vector, so if you only consider that vector, it will be a 1 by 2 vector. A 1 by 2 vector, when you multiply by a 2 by 5 vector, you will get a 1 by 5 vector. And that will be this last row. So that will be the attention scores for the not key equal to ball, but query equal to ball. So you can even individually pick up vectors from this and multiply with the transpose of key to get the corresponding attention score. Now, once you get attention scores, they are not attention weights. You convert the attention score. So this is not key, query. These attention scores are scaled by 1 by square root of d. D of what? D is the dimension of the key space, 1 by square root of dk. In our case, it's 1 by square root of 2. The reason why we are doing this is because we want the variance to be 1. I will explain this in a short moment. Why exactly does 1 by square root of d scaling works, or why is it not 1 by d, or why is it not some other number? We'll explain. I'll discuss that in a moment. But after this scaling is done, the numbers in this vector will reduce, right? Because now you are dividing by some number that is greater than 1. And then you take softmax operation. So after you take the softmax operation, you get attention scores for the query ball. Now these are attention weights, not attention scores, because they sum up to 1. Now attention weights are what we need to construct the final context vector corresponding to ball. Now it's a good time to take a look at what is value. In the simplified self-attention we implemented in the previous lecture, do you remember what we had done? What we had done was, we said the context vector equal to attention weighted sum of the input vectors. Sum of input vectors, right? So if we were considering the context vector corresponding to one particular query, we looked at all the attention weights between that input query and all the keys, and then we got the attention weights. So first we got the attention scores, then we normalized it to get attention weights, and we simply multiplied the input vectors with the corresponding attention weights and then added them up. So we were as if we were doing some vector addition. And this vector addition resulted in a new vector, and that vector was the context vector. And this we could do for every single vector in the input sequence. This is what we did in the simplified self-attention. Here also we are going to do attention weighted sum of some vectors. However, we are not going to be using attention weighted sum of the input vectors, but we are going to be doing attention weighted sum of transformed input vectors. What do I mean by attention weighted sum of transformed input vectors? What I mean by that is, we won't be using input vectors directly. We will be using input vectors that have been transformed into the value space. So the transformed input vector in the current example that we are considering will not have 3 dimensions. It will have only 2 dimensions. And we take the attention weighted sum of this two-dimensional vectors in the value space to get the final context vector. So context vector will also have only 2 dimensions. In GPT, after the vector comes out of the multi-head attention, its dimensionality is retained. Dimensionality does not reduce. Here, actually, the dimensionality is reducing from 3 to 2. But don't worry, this is just an example, right? In reality, most large language models will not change the dimensionality of the input embedding as it passes through the multi-head attention. Now, let's discuss a little bit why square root of d. Why exactly did we divide the numbers by 1 by square root of d? So there are 2 reasons for this. First one is softmax. When we take softmax of some big numbers or scale numbers, it can become very steep. Let me first demonstrate to you that in code, what I mean by that. And then I can show you the rest of the code. So first let's discuss what happens when you scale some numbers. So let's consider these set of 5 numbers. Okay. So let's say I have a tensor or vector with 5 numbers. And if I simply take the softmax, I get the result is this. It becomes a probability distribution and sum total of these numbers are 1. And it will also, the numbers will also be between 0 and 1. Now let's say I multiply all these numbers by 8. So basically I am multiplying it by a scaling factor. When I multiply this by a scaling factor, look at what happened to my softmax. My softmax distribution now, again, it will sum up to 1, but it is now so much sharp because these numbers are now so small. The fifth number is now much bigger. 80% is the fifth number, but these numbers became so small. On the other hand, the softmax before scaling was a bit more, even distribution. So during the training of large language models, we don't want the final dot product output to be, such a peaky kind of numbers. We don't want such peaky numbers. We want numbers that look more like this. So to prevent softmax from giving us outputs like this, we have to scale the numbers appropriately. So if the original set of numbers were these numbers multiplied by 8, we had to divide those numbers by 1 by 8 to get good set of softmax numbers, distribution numbers like this. So only then we can say that, okay, this much 14% attention is paid to this, 20% attention to this, etc., etc. We don't want the entire attention to be just paid to one token. We don't want extremely peaky distribution of the softmax. So that is one reason. Second reason is that we want to make the variance of the dot product of query multiplied by key transpose somewhat stable. I'll show you this with a simple example. So here in this code, what I'm doing is I'm generating 1000 set of random query and key matrices. So q equal to np.random.randn will generate from a normal distribution. It will pick n number of random numbers corresponding to whatever dimension we feed. So if we say I need a 5-dimensional query matrix, this will generate 5-dimensional query vector, which are random numbers. And then I will do that 1000 times. And then what we are printing here is, we are printing the variance of the resulting dot product. Dot product of what? Dot product between query and transpose of key. So if I have a query vector of, let's say, 5 dimensions, and I have a key vector of again 5 dimensions, I take the query multiplied by transpose of key. So that will be simply one number because dot product between 2 vectors will be one scalar. So if I'm conducting 1000 experiments, I will have 1000 dot products, right? And this itself we can do for 2 different dimensions, for a dimension of 5-dimensional query and 20-dimensional query. Okay, so let's keep this as 20. This is 20. Okay, so now let's run the code and see what happens. Okay, so just see this. The variance of my dot products, if the dimension is 5, is around 4.56. So it's on the order of 5. Variance of the dot product for a 20 dimensional space is on the order of 20. Right? So here you can see that as the dimensionality of my key query value space increases, the variance of my Q dot key transpose, the variance of my attention scores are now increasing. I don't want this because this will result in unstable training. Because what if my dimensionality of the key query value space is 128, or if it's on the order of 100, what will happen? I can simply change these numbers to 100. So 100. So now the dimensionality is 100. See, my variance before scaling now became on the order of 100. So as the dimensionality increases, the attention scores, which is the dot product between query and key, becomes so much it will experience so much variation, which is not good for the LLM training. So what I want is I want some stability. I don't want these numbers to experience so much highly scalable variance with respect to my dimension of the key query value space. So if you divide by square root of d, so here, for example, just see this line, scaled dot product equal to the actual dot product between query and key divided by NP. NP is numpy dot square root of whatever is the dimension. So 1 by square root of d. When you do that, look at the scaled numbers. So variance after scaling for 5 dimensions, it's close to 1. Variance after scaling for 100 dimensions, it's also close to 1. Now, what if I had not put 1 by square root of d? What if I just put 1 by d? What will happen to the variance in that case? See, when I divide by 1 by d, the variance is again not scaling approximately close to 1. See, now as you increase the number of dimensions, your variance is decreasing. So the variance for your 5-dimensional query space was 0.18. Variance for 100-dimensional query space was 0.01. This is also not good. You want stability while training, and the stability should not be affected by your choice of number of dimensions in your key query value space. So that is the reason why you divide by square root of d, because when you divide by square root of d, your variance is also scaling by square root of d. So the scaling happening in the variance will get cancelled out because you have a square root of d division happening. So this is why we are dividing exactly by square root of d before we pass the attention weights into softmax function. Now, just to recap what all we discussed, we had input vectors, and we discussed that simple dot product was what was done. Before, in simplified self-attention, we took simple dot product, but we saw the issue with respect to simple dot product for calculating attention scores, because simple dot product sometimes may not give us good attention scores, which will help us eventually to get good context vectors. So simple dot product was not enough. So we decided we will not be taking simple dot product. We will be rather taking dot product of something else. And what is that? We will be taking dot product of transformed input vectors. So we defined 2 transformations, one transformation for queries and one transformation for keys. For that, we defined the query matrix WQ and key matrix WK. Our input was 5 by 3 in the example that we took, because we had 5 words in the sequence and the vector dimension was 3. It was in a 3-dimensional space. But this WQ was 3 by 2 dimension, WK was 3 by 2 dimension. So the resulting query matrix and resulting key matrix was of dimension 5 by 2. So what happened was my 5 by 3 input sequence got transformed into 2 separate set of sequences. One sequence corresponding to query in a 2-dimensional space, another set of sequence in the key space, which is also 2-dimensional. Then what we said was, instead of taking softmax of the query.key transpose, so query.key transpose is the dot product, we take the scaled dot product. So we do the dot product, but then whatever we get, which are called the attention scores, we scale it by dividing by square root of the dimensionality of the key space. And then we take softmax of this. So softmax of Q dot K transpose divided by square root of dimensionality of the key space. And what does this give us? This gives us attention weights. And if you go to the paper, that is exactly what you have in the bracket, in the softmax here. So softmax of Q times key transpose divided by square root of the dimensionality of the key space. Now comes the value. So I hope you are now able to make better sense of the equation presented in the attention is all you need paper. Now what do we do with this attention weights? In our vanilla dot product, so let me just delete this thing. In our simplified self-attention, we use these simple dot products as the attention weights, as the attention scores. Then we used softmax to convert that into the attention weights. And then we use these attention weights to multiply the attention weight with the input embedding. So this input embedding was directly used so that we constructed an attention weighted input embedding to create the context vector for any given query, right? However, that is not what we are going to do here. We have the attention weights, and instead of multiplying these attention weights with the input embedding X, so if we were not having the value matrix, what we would have done was softmax of Q dot key transpose divided by square root of dimensionality of the key space multiplied by X, where X is the input embedding. This is what we would have done. Something like this. Not exactly this, something like this. But in the paper, you don't see, you are not directly multiplying with X. You are not directly multiplying with the input embedding. You are multiplying with the transformed input embedding so that you can, use trainable weights to change the values of the input embedding to be more suitable to produce a better context vector. So here, instead of multiplying it directly with the input embedding, you are multiplying it with the value vectors. So that is why here you have V. Now, how is value calculated? If we go back to our diagram, value is calculated over here. Value is also a 5 by 2 matrix. Why? Because you have here 5 input tokens, 2-dimensional space. Value space is also 2-dimensional. So you multiply 5 by 3 input matrix with the 3 by 2 transformation matrix. So now this is the trainable matrix for values. So 5 by 3 multiplied by 3 by 2 results in 5 by 2. This is value. Now this 5 by 2 is used to be multiplied with the attention weights. By the way, attention weights was of what dimension? Softmax of query dot key transpose divided by square root of dk. What was the dimensionality of this? We had 5 numbers in the input, which means we have 5 queries and 5 keys, right? So this had a dimensionality of 5 by 5. Now this, when we multiply with a 5 by 2, V, so this is now dimensionality of V, this is the dimensionality of this equation, we will get 5 by 2 dimensional context vectors. 5 by 2 dimensional context vectors meaning there are 5 vectors, each vector has a dimension of 2. How many vectors did we have in our input sequence? We had 5 vectors. And our goal was to produce context vectors for every single vector in the input sequence. We wanted to construct context vectors corresponding to every single vector in the input sequence. Input sequence was of a dimensionality 3 because it was in a 3-dimensional space. But then we decided to transform it into a 2-dimensional space using key, query, and value weight matrices, which are trainable matrices. So at the end of the day, we are expecting 5 context vectors corresponding to each input token, but the dimensionality of this, the new space will be 2-dimensional, which is why it turns out to be 5 by 2. So now let's go back to the numbers that we had to see how this looks like. So the numbers that we were looking at was this, right? So we had scale attention scores and then we got the attention weights. Now these attention weights are the attention weights for ball. But now what we want to calculate is we want to calculate the context vector corresponding to ball. Context vector will be a two-dimensional vector. How do we get the two-dimensional vector? This 1 by 5 matrix will be multiplied by, so these are the attention weights. We multiply this by what? We multiply this by value matrix. Value matrix is 5 by 2. And where is that? Value matrix is over here. This 5 by 2 matrix. So let me go back here. So the context vector is normalized attention weights. Not just normalized, you scaled the attention scores by square root of D. Then you took the softmax. So this became attention weights. Now you have how many attention weights? Attention weights are 5 by 5. If you look at just the attention weights corresponding to one query, it is simply 1 by 5. So here the query is ball, so it is simply 1 by 5. Value matrix, you have 5 value vectors and each vector has a dimension of 2. So value matrix was of dimension 5 by 2. So 1 by 5 multiplied by 5 by 2 will be 1 by 2. So these are the attention weights for ball. So this is how much attention ball should pay to dog, chased, and ball itself. And this is the value matrix. So this is the value vector corresponding to the value vector corresponding to a dog, chased, the ball, and 1 by 5 multiplied by 5 by 2 will be 1 by 2. So now this is the context vector for ball. The initial vector of ball was this. The input embedding of ball was this 1.2, 1.7, 1.5. So it was a three-dimensional vector, and it had some information present in it, but it had no context because this was purely the semantic meaning associated with ball. It did not carry the information or the fact that dog, chased, etc. Those words are also present in the sequence. That information was not present in the input sequence. But now, finally, when this guy, this 1.2, 1.7, 0.5, by the time it gets transformed through the query key value matrices and through attention weights, and finally when it turns into a context vector, you have these numbers 1.41, 0.91. Like that, I have context vector for dog, chased, and finally ball. So there will be 1 by 2 for 1 by 2 for chased, 1 by 2 for dog, and 1 by 2 for the initial which means the final matrix that results will be a 5 by 2 matrix. And it would look like a 5 by 2 matrix where the first row corresponds to the context vector for the dog, chased, the ball. And what was the initial token embedding? It was this. It was a 5 by 3 matrix. Initial embedding of the 5 tokens were each 3-dimensional. Then there were 5 such tokens. So each of them looked like this. And then finally they got transformed into a 5 by 2 set of, 5 set of 2-dimensional context vectors. So this is exactly what we do with the value matrix. So we use value matrix like this. Let's go down. So these are now the attention weights. So attention weights are multiplied with my value matrix. Inside the value matrix, there are 5 value vectors, each value vector corresponding to each token. Each token has a dimensionality of 2. So 5 by 5 matrix multiplied by 5 by 2 matrix results in 5 by 2 matrix. Now these are the context vectors corresponding to my 5 input tokens. Each input token was of 3 dimensions, but now it became 2-dimensional. Now this context vector is now much more useful because it's much more rich in context or in meaning. Now let's do one thing. Let's implement all of this in code, right? And then we will come back and discuss a few more things. But just before proceeding ahead, so if our attention weights are like this, so ball should pay 10% attention to 30% to dog, 30 to dog chased the ball. Then we multiply that by V to get the final context vector, right? So we will discuss this diagram in a little bit, but let's first go to code and try to implement this whole thing one by one. So this is my new input sequence, dream big and work for it. So there are 6 numbers in my sequence, but my input dimensionality I'm still keeping as 3 dimensions. So it's easy to plot. So I'm using PyTorch so that we can construct these tensors. So this is corresponding the input embedding of dream for big and work for it, right? So these are the words. Let's just run this so that it's initialized. Now, if I want to get the vector corresponding to, let's say, the second word in the sequence, which is big, I just need to say inputs of 1 because Python indexing starts from 0. So inputs of 1 is the vector corresponding to the second token. So if we say print x_2, we can see that vector. So 0.75, 0.2, 0.55, which is exactly this guy, right? So the shape of these vectors also we can print d_in. So the dimensionality of the input sequence is 3 and dimensionality of the output sequence, which we are defining to be 2. And what does it mean by dimensionality of output sequence? I just simply mean dimensionality of the context vectors, which results from the key query value operations. So dimensionality at the output is 2. So this is my input vector corresponding to big, which has 3 dimensions. And now we are trying to convert this into a 2-dimensional context vector. Okay, so first, let's start by randomly initializing the weight, the key query and value weight matrices. So here torch.rand will create a random number matrix of the dimension d in comma d out, which will be 3 by 2. And this will construct 3 matrices: query matrix, key matrix, and value. Here the seed 1, 2, 3 is provided for code repeatability, so that although it's a random number generator, we are seeding the random number generator with an input seed, so that same random numbers will be generated irrespective of who is running the code. If you don't provide this, each time it will produce different random numbers. So if I run this, it would have produced now the WQ, WK, and WV matrices. Now we can print a sample matrix here. So if we print W query, the query matrix is 3 by 2. Why 3 by 2? Because my input numbers are 5 by 3. I have 6 by 3. I have 6 words in the sequence, and each word is 3-dimensional. So now I have 6 words. In my previous example, there were only 5 words. So 6 by 3 is the input. 3 by 2 is the WQ, which means the output will be 6 by 2. Because I'm converting 6 input tokens in a 3-dimensional space to 6 vectors in the query space with 2 dimensions. Similarly, W key will also be 3 by 2 and W value will be 3 by 2. And these are random numbers generated from the random number generator. Now, if I want to pick the converted query for the second item in the input sequence. What is the second item in the input sequence? It is big. So I want to see how this big is transformed in the query space. So what happens to this big in the query space? It will, of course, become a 2-dimensional vector. That much is clear. Now, what would that 2-dimensional vector look like? To know what it will look like, all I need to do is I do x_2 multiplied by the query weight matrix. So this will be the query corresponding to the second token. This will be the key corresponding to second token, which is x_2. By the way, x_2 is this. We had already defined it here. x_2 is the first row in the input sequence, which is the input vector corresponding to big. And x_ multiplied by W value. So this at signifies matrix multiplication in Python. So x_2 multiplied by W value will give us the value vector. So now this is the query vector corresponding to big. And we can also print the key vector corresponding to big. This is a key vector corresponding to big. and this is the value vector corresponding to big. Every single one of them will be of 2 dimensions. So this is the key vector for big. This is the query vector. Sorry, this is the query vector for big, key vector for big, and value vector for big. So this is how the 3-dimensional big vector is converted into 2-dimensional vectors in the key, query, and value space. Now let's calculate the entire QKV matrix, not just one vector. Like that, we should have 6 vectors because we have 6 input words in the input sequence. So keys are nothing but, so instead of just picking one of the items from the input, instead of picking just one row from the input, take the entire input matrix. Entire input matrix was 6 by 3 dimensions. W key was of 3 by 2 dimensions. So key will be of 6 by 2 dimension, value will be 6 by 2, query will be 6 by 2. So here when we print the shape, you can see that the shape is 6 by 2. We can also print the actual numbers. So print keys, then print queries, and print values. These will be 6 by 2 dimensions. So this is now the key matrix, query matrix, and value matrix. So if I just focus on query, this is the query vector corresponding to dream, big, and work for it or something, right? Sorry, this is dream. Dream, big, and work for it. That was our sequence. So now these are the 6 vectors in the query space corresponding to 6 vectors in the input sequence. Now let's pick just one query and one key and see what is the attention score between them. Not attention weight, just the attention score. Now please remember, what is the attention score? Attention score is nothing but dot product between query and key, right? So if we take one particular key and one particular value, one particular query. So one particular query that we are taking here is query underscore 2. Query underscore 2 is this guy. Query underscore 2 is query corresponding to the input word big. Then key underscore 2 is key corresponding to the input word big. So keys of 1 means key corresponding to big. Keys of 0 would have been key corresponding to dream, big, and work for it, right? So keys of 3 means dream, big, and work. So it will be corresponding to work. So here we want to see the attention score between big and itself. If you want the attention score between big and itself meaning between big and big. Big is the query, big is the key also. It will be keys of 1, and attention score between second query and second key. So that is why it's called attention score underscore 22. It is 0.6990. So in the attention score matrix, this item should be where? This should be along the diagonal. Why? Because our attention score matrix will look like this. Dream, big, and work for it. Then same thing goes here. Dream, big, and work for it. Now, if my query is big, and if I'm trying to calculate the attention score between big as the query and big as the key, it will be here. This is the position, right? So in my final attention score matrix, which will be a 6 by 6 matrix, the position will be second row and second column. So we'll see whether the second row, second column items value is, whether it's 0.6990 or not. That we will check. Now, we can also calculate attention score between big and every single token or every single key. That will be the query, which is big, multiplied by the entire key matrix. So entire key matrix is keys, and then you are taking transpose of that as the matrix multiplication. So here we are just taking the key vector corresponding to big, and you are multiplying it with the, query vector corresponding to big, and you are multiplying that with the key matrix to get the attention score. So now these are the attention scores, which denotes the attention big has to pay with dream, big, and work for it. Now, obviously, these attention scores will not add up to 1 because we have not, first of all, normalized. We have not scaled it. We have not passed this through softmax. So these will not add up to 1. Now, if I want to see the whole attention score, I can simply run this. So attention scores are nothing but query multiplied by key transpose. Query is a 6 by 2 matrix. Key is also a 6 by 2 matrix. When you transpose it, it will become 2 by 6. So queries multiplied by key transpose will be 6 by 6. And let's just check the second row and second column, which will be this item. See, this is the attention that big as a query pays to itself, right? And we calculated it here. This was 0.6990. And here indeed, you can see that it's 0.6990. So this is now the attention scores for big. This is the attention scores for dream. So dream, big, and work for it. So if I suddenly ask you, how much attention should it pay to dream? It is the last item in the sequence, which means you will go to the last row. And how much attention should it pay to dream? And dream is the first item, which means this is the attention score that you have to look at. So dream will be looking at it will be looking at dream with an attention score of 0.6680, which means it is attending to it. It's giving that much importance. Now, these numbers are okay in terms of importance, but it's not giving us an interpretable picture. For that, we have to scale it down by square root of d and take softmax. So we first divide these numbers by square root of d. And let's see when we divide just these numbers by square root of d. And here d is 2. Two-dimensional space is what we are considering in our key query value space. So we'll divide by square root of 2, which is 1.414. So when you divide, instead of now these numbers, so let's do one thing. I will just copy paste this here. So print both attention scores and attention weights. So the first set of numbers are attention scores corresponding to big. These are now attention weights corresponding to big. And here you can see that we have divided by the square root of the dimensionality of the key space. And we have also taken softmax from the PyTorch library. So these are now the normalized, or these are the attention weights. And this will sum up to 115 plus 15, 30. This is 40 plus 8, 48 plus 48 point something. 58, 65, 75, 81, 91, 98, and some residue, some remaining numbers will add up to 100. We already discussed why we are dividing by square root of d for two reasons. One is softmax. We don't want the softmax numbers to peak. And second is we want the variance of the dot product between query and key transpose, which is basically the attention scores. We want the variance of those numbers to be close to 1. So that's the reason why we are dividing by square root of d. Now that we have the attention weights, we just have the attention weights for big. We don't have the attention weights for all tokens yet. For that, we have to do what? Instead of query underscore 2 multiplied by keys dot transpose, and instead of just normalizing attention weights for just the second item, we have to do that for all items. So instead of attention scores underscore 2, I should do something like this. Attention scores equal to query multiplied by keys dot transpose. And then here I should use attention scores and divide by square root of dimension and call this as attention weights, and then print attention weights. This I can delete. If I do something like this is queries, then I should have attention weights. So let's run this. Now these are the 6 by 6 attention weights, and each row will individually sum up to 1. So how do we ensure that each row is actually summing up to 1, not each column? By giving this parameter. So dimension equal to -1 ensures that equal to -1 means you will look at the last dimension of whatever tensor you have. So here you have a 2-dimensional matrix. So last dimension is column. First dimension is row. Second dimension is column, which means last dimension is column. So you will apply the softmax such that each row will sum up to 1. So now the sum of these 6 numbers will be 1. Sum of these 6 numbers will be 1. However, the sum of the first column will not be 1. That you can try yourself. This is 15, right? 15 multiplied by 6, or You can pick anyone. Yeah, see this 17. These are all 17. 17 multiplied by 6 is what? 17 times 2 is 34, 51. This is definitely greater than 100. So these are the attention weights. So I have the code once again written here for attention weights. This we have already discussed. So attention weights. Let's come back to the attention weights, entire attention weight matrix a little bit later. Let's first focus on the attention weights for the second item, which is big. So attention weights 2, query underscore 2. Okay, so this is what we wanted. So now we have the attention weights corresponding to big. And now let's calculate the context vector corresponding to big. So context vector is nothing but attention weighted values. In the simplified self-attention, it was attention weighted input vectors. But here we don't use input vectors directly. We use transformed input vectors. So it is attention weighted values. So attention weighted values are this. So these are the attention weights for the second item, which is big, multiplied by the value matrix to get the context vector corresponding to big. So now the context vector corresponding to big is this, which is in the 2-dimensional space because our key query value space is 2-dimensional. So now our input vector, which was big, which initially had these numbers, where is big? Big was these three numbers, 0.75, 0.2, 0.55, got transformed into a context vector, which has much more information about what other words are next to it, like in this format, right? So this is what we can do. And if I want the context vector for all the inputs, input numbers, what I can do is attention underscore weights. I can just bring this code from here. So attention weights equal to torch.softmax of attention scores divided by square root of D. So D multiplied star 0.5 means it's square root, D raised to 0.5. And then attention weights are these, and I don't want to print this. So if I do this, I got 6 by 6. And then here context vector, the entire context vector will be context underscore vector equal to attention underscore weights multiplied by values vector, values matrix. So values matrix was 6 by 2. Attention weights is 6 by 6. So 6 by 6 matrix multiplied by 6 by 2 matrix resulting 6 by 2 matrix. And I can print just the context vector. So this should be what? I should have 6 vectors of each dimensions 2. It should be 6 by 2. So if I print this, this is 6 by 2. This is the context vector for dream, big, and work for it. So at the starting, we had 6 input vectors, each 3 dimensions. Now we have 6 context vectors, each 2 dimensions. We can also convert this whole operation into a cleaner Python class. So in Python class, we can simply say class self-attention. So this self-attention v1 is just one Python class that we have defined. I'll show you one more variant of the same Python class. So we initialize the random weight matrices for query, key, and value. So this nn.parameter is one way to do that. But in another Python class, we are using nn.linear. So for neural network training, to initialize these numbers in a much more optimized way, which also includes bias. So usually when we are multiplying with weight matrix, we just don't have weights, right? We also add bias. So usually in neural network, we have weights parameters, which multiplies with the input, but then we add that with bias, right? So here we also introduce bias, but I don't want to spend too much time on this. All I want to show you is that whatever we have done above can now be summarized into maybe like 10-15 lines of code. So we initialize the random weights for query, key, and value. Then key is equal to input multiplied by W key, query equal to input multiplied by W query, value equal to input multiplied by W value. So self.W value is the way classes reference to that particular instance of this variable. And all we need to do now is, if we define a class like this, and if we want to run this operation again and again and again, we just need to instantiate the class by creating an object. So that's the reason why in Python, many libraries define functions inside classes so that you can define instances of those classes as objects and use it as many number of times. Then attention scores are query multiplied by key transpose. Attention weights, for attention weights, what you do is attention scores are divided by square root of D, and then you take softmax. And then attention weights are used to multiply with the value matrix to get the context vector. That's you get the context vector now. So I hope this part is very, very clear. You should definitely try running some similar version of this code yourself. Now, although the weights are trainable, we are not going to train it right now because then we'll have to define the entire large language model architecture and define backpropagation and everything. But just understand that the random numbers that we initialized in the weight matrices for query key and value, those will not be random after training. Those numbers will evolve to produce better and better context vectors. Now, let's go back to the nodes. So how is input embedding now converted into context vector? So let's say these are our input embeddings, these vectors. This is the input embedding for the. So now we are back to our other sentence. The dog chased the ball. Okay. The dog chased the ball. Okay. And now let's say I want to calculate the context vector corresponding to ball. So now ball is my query. So first what I will do is I will calculate attention weights and I will multiply. You can imagine these vectors being multiplied by your corresponding attention weight. So the will be multiplied by the attention weight between the and ball. Dog will be multiplied by the attention weight between dog and ball. Chase will be multiplied by the attention weight between chase and ball. So if the attention weights are like this, 0.1, 0.3, 0.3, 0.1, 0.2, these numbers add up to 1, 0.6, 0.7, 0.8, 0.9, 1.0. So this is now the attention weights corresponding to ball. So how much attention ball should pay to each vector, right? So you can imagine it to be something like this. In the simplified self-attention, what we did was we multiplied the initial context vectors with these numbers. Initial context vector was multiplied by 0.1. Initial context vector was multiplied by 0.3. And this is the context vector for the is multiplied by 0.1. Dog is multiplied by 0.3, which means the length of the dog will be reduced to 30%. Chased will be multiplied by 0.3, which means length of that vector will be reduced to 30%. This will be reduced to 10%. This will be reduced to 20%. And then you will get these attention weighted or attention multiplied vectors, these 6 vectors or 5 vectors rather. Then you add all of them to get the final context vector. So this is what we did in the simplified self-attention. In the current self-attention, which is self-attention with trainable weights, most of the things remain the same, except the only difference is now this is not the input embedding anymore. This is the value vector for the. This is the value vector for dog. This is the value vector for chased. This is the value vector for the, and this is the value vector for ball. Then these numbers 0.1, 0.3, 0.3, 0.1, 0.1, 0.2 are the resulting attention weights which came from the dot product between query and transpose of key. Then we did square root of dk and we did softmax. So these attention weights are the result of this mathematical operation. Then what we do is these value vectors are scaled using these attention weights, and then you sum up those weighted vectors. So then again you sum up those weighted vectors to create the context vector for the ball. So basically whatever you get from this, you multiply that with your value vector. So this is now a matrix. This is not a single vector anymore in this equation. So that is what you have in the attention is all you need paper. Now, if you go back to that equation, right? How do you read this formula? What does this mean? Attention of query, key, and value. What this means is if you have an input sequence, how much attention should each token pay to all the tokens in the input sequence when you convert those tokens into query, key, and value space? That is the question that we are asking here. So tokens are not anymore in the input embedding space of 3 dimensions in our example. It is in 2 dimensions because the query, key, and value space are each in 2 dimensions. So how much attention should each token pay to rest of the tokens in the input sequence? The answer to that is the amount of attention that we should pay should be such that you are calculating context vectors. So every single vector in the input sequence is converted into a context vector using this formula. So this is the formula for getting the context vector. And how is that done? Context vector is created from value vectors. Are value vectors directly used for getting the context vector? No. Value vectors are scaled and added to get the context vector. And how is the scaling done? Scaling is done using attention weights. How are the attention weights created? Attention weights are created by taking query.key transpose, and to get more stable variance, you divide by square root of the dimension of the key space, and then you take softmax so that you have weights summing up to 1 for every single token. So those weights for every single query, you will have, let's say you have 5 queries, meaning 5 input tokens. You will have, for every query, you will have 5 attention weights. So you sum up the values, which are again 2-dimensional vectors. You will have 5 2-dimensional vectors. You sum up those 2-dimensional vectors according to corresponding attention weights. So you multiply attention weight with one query vector, you multiply attention weight with the next attention weight with the corresponding query vector, and then you add up those vectors to get the resulting context vector of your input sequence. So if we were to write in terms of dimensionality, the dog chased the ball. So this is an input sequence with 5 words. The dog chased the ball. Each word is represented by a 3-dimensional vector. Then this is multiplied by WQ, which is 3 by 2, to get a 5 by 2 matrix, which is the Q matrix. This is multiplied by WK, which is a 3 by 2 matrix to get a 5 by 2 matrix, which is the key. This is also multiplied by W value, which is 3 by 2 to get 5 by 2. These are 5 value vectors. So these are 5 Q vectors, 5 key vectors, and 5 value vectors. Then you take the dot product of these two such that Q dot key transpose will give you attention scores. So you will have a 5 by 5 matrix, 25 attention scores. Then you divide these attention scores by square root of D, and then you pass it through softmax to get attention weights. So this will again be a matrix of dimension 5 by 5. Then what do you do with these attention weights? Do you multiply that directly with the input embedding? No. You use that with the value. So your value is now 5 by 2 and your attention weights are 5 by 5. You multiply these two matrices to result in a 5 by 2 matrix. Now what is this matrix? These are 5 context vectors corresponding to your 5 input tokens. So you had input tokens for 5, but they were in a 3-dimensional space. Now all of them or each of them are converted into corresponding context vector. Now the context vector, each of them has a dimension of 2. This is what happens in the self-attention using trainable weights. So I hope from here on, whenever you look at this equation, softmax of Q dot key transpose divided by square root of D multiplied by V, I hope you will never be scared anymore. Instead, you will think about it from a intuition point of view. So why did we introduce query, key, and value? Because directly multiplying input embedding, directly taking the dot product between input embedding was not good, because it can result in, as you saw in the example of the dog, it should have paid more attention to ball than dog. But because you are taking direct dot product between vectors, your context vector was not very good, or attention scores were not very good. But so to improve your attention scores or improve the attention weights, you converted or you transform the input embeddings or input vectors into another dimensional space, which is the query key value space. And then using that space, you construct the attention weights using Q and K. And then those attention weights are multiplied after scaling down with square root of D and after converting to softmax, that you multiply with value. So this is why it's called scaled dot product attention. So where is dot product coming? Dot product is coming in Q dot K transpose. Where is scaling coming? Scaling is coming in square root of D. And where is attention coming? Basically, these are the attention weights. And these attention weights are multiplied with value to get the context vectors. And finally, before we wrap up the lecture, why these names, query key and value? What are the origins? Query is like something you're looking for, meaning if your sentence is dream big and work for it, and if big is the query, you're looking for what should big do, right? So big is your query. Then key is all the inputs in your sequence. So basically, how much should this particular query pay attention to all the different items you have available in your data set. So you have all the input sequences in your data set, and key will help you identify which one should pay most attention to query. Should dream pay most attention to big? Should work pay more attention to big, etc. And then value is the actual information itself, which you are trying to retrieve. What do we mean by that? The value matrix was the actual transform matrix of your input embedding, right? So you are trying to retrieve information from the value space, from the value matrix, such that you are taking a attention weighted sum of that. So value, so let's just go through this one. Query is the current token, current word or token that has a question about its context. So if my sentence is dream big and work for it, and if I'm trying to understand how much attention should big pay to each of the words in the sequence, I am having a question about the context of big, which means query is big. It is asking, what should I pay attention to? Should I pay attention to dream? Should I pay attention to work, etc.? Key is basically saying, I don't know finally what the context vector is, but I can tell you how much attention, or I can tell you I can tell you what the big is related to. So if key is dream, then I can say, and if the value between them is 0.2, then it's saying big should pay 20% attention to dream. If key is and if the number is 0.3, then it says big should pay 30% attention to and, etc. And then value is, here is the meaning of the content you will get if you attend to me. So basically, value is is in a new transform space. So if you have 5, if here you have 1, 2, 3, 6 tokens in a 2-dimensional space, so you have now a value space in which each of the input embeddings are converted into this value space. So value space basically embeds the actual information that is there in your input sequence. And then that value space can be used to construct the final context vector. Now, so far, what we have discussed in this series is Badano attention we have discussed, simplified self-attention using just basic dot product we have discussed. And in the current lecture, we also discussed the self-attention with trainable weights. But still we are having to go one more step to reach the attention mechanism used in GPT-2 or 3 or other models, which is masked self-attention or causal attention. So in the next lecture, we'll be discussing masked self-attention. But I hope you understand the intuition behind query key and value. And I would say you already have 90% of what is required to understand masked self-attention. So the next lecture you will find relatively simple if you have understood the current lecture. One thing I would like to say is there is a lot of technical things that we discussed in the current lecture, and this has been also quite a long lecture. So if you have reached till this point, you have had so much patience and you have had so much interest to understand this topic. So I recommend you go through this material again and again, as many times as needed, take proper notes, and try to, implement the same in code. The code is not at all difficult. You might have seen it. It's very beginner level code, basically. We did not do any deep learning to implement it in deep learning. Although we said these are trainable weights, we actually did not train them. So the code was pretty simple. Concepts are actually fairly intuitive. It's just that you have to spend a little bit more time, right? So I highly recommend you pause wherever you wanted to pause and rewatch sections which requires clarity. But more importantly, try to zoom out sometimes and try to understand the big picture. We discussed about tokenization. We discussed about importance of how tokens should pay attention to each other. And then now we are understanding through today's self-attention that tokens you cannot be directly used in the dot product. Tokens need to be transformed before we do anything with the dot product. But the idea of dot product still remains. Dot product is still a valid operation because it tells you how close to each other these vectors are, or semantically how close to each other the vectors are. So I hope you understand the intuition behind these things. Thank you so much for listening. I'll meet you again in the next lecture. Take care until then. Bye.